Cryptography, the study of codes or how to secretly communicate without anybody else knowing your message. When we think of codes, we often think of spies, detectives, and secret messages. But did you know every time you buy something online, cryptography is being used? This is a credit card. These numbers are like the keys to your bank account. Anyone with these numbers will be able to access your account and take money from it. Therefore, it is imperative that no one except for the store will be able to see those numbers. So, how do you give your credit card to the store to buy something without anybody else being able to see it? Well, you could encode your credit card number. Your credit card number 10 could be encoded into 32 using the cipher. Then you send the cipher and 32 to the shop, and the shop will use the cipher to decode 32 back into 10. And if anyone stumbles upon 32, they will not know it is your credit card number. This is equivalent to putting a message in a box, locking that box, sending the key and the lock to the store. But the downfall is that the key could easily be stolen, and that's similar to how anyone can know, steal, or figure out the cipher and know your credit card number. Here comes public key cryptography. In terms of boxes and padlocks, this is what happens. Anyone who wants to send a message to their bank can get a box with an open padlock. The customer puts their credit card number into the box, locks it shut, and then sends it back to the store. No one will be able to open it and no one will have the key except for the shop. How can we do this with numbers? The answer is in using a one-way trapdoor function. In cryptography terms, it means it is very easy to encode something, but impossible to be decrypted unless they had a crucial piece of information known as the trapdoor. For example, let's say you're a chef sending a secret ingredient to your brother, and that ingredient is salt. The trapdoor here is pepper. You mix the salt with pepper, and when your brother receives the mixture, he's able to sieve away the pepper and know it is salt. However, Kelvin, a rival chef who stole the mixture, would never be able to separate the mixture, as he would never know that the trapdoor is pepper, and hence would never know which sieve to use to separate the mixture. Here we see it is easy to disguise or encode the salt. However, it is hard to decode or separate the mixture. This is how public key cryptography conceptually works. The mysterious powder is the public key. Anyone can use this to encode the message and send it to the store. Knowing that the powder, and hence which sieve to use, is the private key, only the store knows this and is able to decode your message and obtain your credit card number. RSA cryptography is a common type of public key cryptography, named after the surnames of the 3 MIT mathematicians who discovered it. Here's how it works. The store gives out 2 numbers, E and N, the public keys, and you use these 2 numbers to encode your credit card number. C is your encoded result and A is your credit card number. Then the store uses C and the private key, D, to get back A, which is your credit card number. Modulus arithmetic is basically division that only cares about the remainder. For example, 46 divided by 8 equals 5 with a remainder of 6, and hence 45 mod 8 is 6. So how do you derive E, N, and K? Let's explain this with real numbers. Take 2 prime numbers. In real life, these primes are hundreds of digits long, but for simplicity's sake, let's use 3 and 7. Multiply them together to obtain N, and N is the first part of our public key. Now, you need to know phi n, which is always totient function, is simply how many numbers from 1 to n minus 1 that are relatively prime to n. We can work out phi n with p minus 1 times q minus 1. 2 times 6 equals 12. Now, E, the next part of the public key, is a number which is relatively prime to phi n. Let's use 29. Now, we have to figure out the private key with something known as Bezo's identity. We have to solve for D and Y, where D and Y are integers. We could use Euclidean's algorithm, but right now, let's just say D is 5 and Y is 12, and we could sub it in to see that it works. So now you have the public keys, which are 21 and 29, and the private key is 5. Now discard everything else, or someone else will be able to figure out D with 2 prime numbers. So let's put this to the test. Let's say you have to send your credit card number to the store. First you encode it, so 10 to the power of 29 mod 21 equals to 19. So the store receives 19. Now he uses a private key to encode it. 19 raised to the power of 5 mod 21 should be equal to 10, and hence the store gets your credit card number, and anyone who has 19 will have no way to know that your credit card number is 10. So why is RSA so secure? As you can see, the private key requires you to have the 2 prime numbers P and Q. Multiplying them together is extremely fast and extremely easy given today's technology. However, factorizing n back into P and Q, that's impossible given today's technology because it requires lots of trial and error, and right now there's no algorithm available to factorize n back into P and Q. Thanks for watching this video. I hope you liked it.